Hi, this is Alex from devstories.eu. Mastering DeepChem, Episode 5 of 15. If you represent a chemical compound as a flat string of characters, you completely strip away the physical topology that dictates how it interacts with the world. Molecules are not linear sentences, they are interconnected structures. To preserve that structural reality in your datasets, you need Graph Convolution Featurizers. When you hear the word convolution, you might picture an image model sliding a filter across a fixed square grid of pixels. You need to drop that mental model. Atoms do not sit in uniform grids. A carbon atom might connect to 4 neighbors, while an oxygen connects to 2, and a hydrogen just 1. Graph operations handle this arbitrary irregular connectivity, and graph featurizers act as the bridge to translate raw chemical data into a format these operations can consume. DeepChem provides 2 primary tools to do this. The first is the ConvMolFeaturizer. This function looks at a molecule and generates an initial feature vector for every single atom. It calculates properties like the element type, the total number of connected heavy atoms, valence, formal charge, partial charge, and orbital hybridization. It bundles these atom-level features into a specific object called ConvMol. This format was designed to feed directly into DeepChem's native graph convolution networks. The second tool is the MolGraphConvFeaturizer. This is the more modern approach and is highly versatile because it outputs a standard graph data object. This makes it the go-to choice if you are passing data into generic frameworks like PyTorch Geometric or DGL. Let us walk through how MolGraphConvFeaturizer handles a simple benzene ring. Benzene consists of 6 carbon atoms arranged in a continuous hexagon. The featurizer processes this structure by splitting it into nodes and edges. First, it creates the nodes. For each of the 6 carbon atoms, it calculates a numerical array of atomic properties, recording the hybridization state and partial charge of that specific atom. These 6 individual arrays are stacked together to form the node feature matrix. Next, it maps the edges, which correspond to the chemical bonds. It builds an edge index, which is simply a list of coordinate pairs identifying exactly which atom is connected to which. It also generates edge features. For every bond in that edge index, the featurizer records structural data. It checks if the bond is single, double, triple, or aromatic. Since we are looking at benzene, the featurizer explicitly encodes the aromatic nature of these bonds, along with whether the bond is conjugated or part of a ring system. Finally, it cacks the node feature matrix, the edge index, and the edge features into a single graph data object. You now have a mathematical graph that retains both the atomic characteristics and the exact topological connections of the original molecule, completely bypassing the limitations of flat vector representations. Here's the key insight. The quality of a graph neural network is entirely bottlenecked by the structural richness of the data structure you feed it. By properly utilizing a graph featurizer, you ensure your model actually learns the underlying chemistry instead of attempting to memorize a one-dimensional summary. Thanks for spending a few minutes with me. Until next time, take it easy.